Okay, so let me just start by saying that I've never really been to like a media public speaking training course or like gone to journalism school or something, but I'm confident that if I had, they would have told me not to eat a peanut butter sandwich in the 10 minutes between speaking and then speaking again. So that was not a good idea. But anyway, I'll try not to, uh, get my mouth too clogged
Learning
up from residual peanut butter. What?
We're all learning agents.
Yeah, this is all part of the COVID learning experience. So let's see where we left off. We went over some FAQs during the break, and then now we're going to talk about inference for the value function. And in the spirit of keeping things as simple as possible, we're going to talk about one-stage problems. Then after this, we'll talk about two-stage problems, and I'll have a brief blurb about infinite horizon problems that'll just be 2 slides long that shows that really it's the same kind of ingredients, it's just messier. So in a one-stage decision problem, we have xi, ai, yi. So these are drawn IID from some distribution P. And so this could be, for example, randomized clinical trial. X is the patient characteristics or feature vector that takes values in some space script X, which is a subset of RP. And treatments here will assume are binary. That's not really critical. It just makes things more convenient. You'll also see throughout this that I will sometimes change the encoding of treatments as to whatever I think is going to sort of make the exposition easiest. So I'll try to point that out if I switch from, say, -1, 1 to 0, 1 or something as we go. And then Y is an outcome, which is like a utility. So it's coded so that higher values are better. And then in this case, a treatment regime or a policy is just a map from script X into A. Okay, so this is a little bit like a contextual bandit problem with 2 arms, although it's in the sort of batch setting. Okay, so we'll define QXA to just be the expectation of Y given X and A. Then the optimal regime, pi opt X, so opt for optimal, is the argmax over A of QXA, or this is one of the optimal regimes, can be defined this way. And let's suppose that we posit some kind of linear model, say QXA indexed by beta, which is X0 transpose beta 0 plus A times X1 transpose beta 1, where X0 and X1 are feature vectors and beta is just the beta 0, beta 1 vectors concatenated. And then we'll assume that we estimate beta using ordinary least squares. So beta hat n is the argmin of the empirical expectation of the squared residual, so y minus q xa beta. And subsequently, the estimated optimal rule then is pi hat of x is the argmax over a of q xa beta hat. And we're going to define the population analog of beta hat to be the argmin of the same expectation, or the squared residuals, but with respect to the data generating model instead of the empirical expectation. So it's important to note, I'm not assuming that the actual expectation is linear, but we are going to do inference for beta star, which is the projection onto the linear approximation space here. Under very weak conditions, root n beta hat minus beta star is asymptotically normal with mean 0 and some variance covariance. This is not the same one in the previous section. I'll often use sigma as a generic kind of covariance matrix, and I'll try to make it clear what I mean.
Larry,
yes.
You have a question about this linear model. It is set up in a particular way, and you're using that A is either taking the values of plus or -1. And there is some sort of redundancy, because then you can say that like you have actually 2 feature vectors, one for action 1, one for action -1, and then you are over parameterizing the beta, or like, I'm like, it's like an alternative parameterization. So it's like, so why this? I guess like you would argue that this is a general linear model where for the 2 actions you have different feature vectors, and then just writing it in this way. But like the parameterization is just a bit unusual, because then the parameter vector for one of the feature vectors, which is x naught minus x1, is going to be beta naught minus beta 1, and for the other one,
oh, this is, oh gosh, okay, hang on. Yeah. So
there is a typo there, but yeah,
oh, okay.
it's just like it's yeah, like I see that like this is equivalent to the model where you would say that you have 2 separate feature vectors, or as many actions you have that many feature vectors, and that's it.
Yeah, it's equivalent. You're right. It is equivalent. This is called the contrast coding. It's sometimes used more often in stats because one of the reasons is that they'll often look at, well, one very simple thing would be that if this term is identically 0, then that means there's no benefit to tailoring, and also and the kind of estimates you would construct in the original, if we had something that was like X transpose, oh geez, beta 1, times indicator that A is 1. I should stop writing because my handwriting's so terrible. Plus, 1 for -1, then the kind of things we care about are contrast anyway, often, and so this just makes some of the inference more convenient.
Yeah. Okay. All right.
Thanks.
Good. Thanks.
Okay. All right. So one interesting thing is when we talk about what do we want to do inference for, well, there's the value of the optimal regime, which would be V of pi opt. And sometimes I will conflate V of pi opt with V of the regime indexed by beta star. But as many of you know, those are not the same thing. Beta star does not have to index if I plug in, beta star in the Q function, take the argmax, it doesn't have to be the optimal policy because there's a mismatch here between the least squares criteria that's being used and the definition of the value function. So sometimes I will conflate those, but they are not necessarily the same thing. But so what might we want to do inference for? We might want to do inference for the value of the optimal regime, say V of pi opt, which is the expected outcome if you were to assign treatments according to pi opt. And we can write this using inverse probability weighting as V of pi opt is the expectation of Y times an indicator that A equals pi opt of X divided by the propensity to assign A given X. So this is basically the Horwitz-Thompson estimator of the value, but this is just expressing this thing in terms of the data generating model. You could have also done it in terms of the Q function, but we'll do this here. So
Eric,
why would we?
There is a question that we're using Q. Is it the same as the Q in general RL? Is it intentional?
Yes. Yeah. Oh, sorry, I didn't see the question. Yes, it is the same. There's only one decision, so it's not like saying we take this action and we do something else in the future. But it is intended to be analogous. So when we do go to multi-stage problems, we'll see a similarity. Yeah. So that was intentional, but it is. And I guess technically the definition is the same, but there are no future decisions. So it's, yeah.
And there was a question on Discord on the lemmas and the sort of the nice examples you showed in the previous part of the talk. Like, where can people look for references? Will you add references at the end of your slides in the final version, or?
Yeah, I'll add some more references to the slides. There's also some of this is discussed in our we have a book on dynamic treatment regimes that came out in just this year with Butch Sietis and Marie Davidian. Shannon Holloway and I wrote a book, and it has some of that in there. But that it's the paper is, well, it's very focused on precision medicine, so it's called dynamic treatment regimes. And so I'll try to find references that are also more general than just the precision medicine kind of focus. But that has all the causal inference stuff in there too.
I guess the question is whether the proofs will be there.
Yeah, I'll send the papers that have the proofs too, or links to the papers that have the proofs with all the detail. Yeah. Good. Thanks. And the paper that I drew all this from, I'll send a link to that too. Yeah. So this stuff, this section here is all drawn from a particular paper with Min Chen. Okay. Right. So why would we care about this? Well, we might want to show the potential for tailoring decision making in a given context. So we might want to show that pi opt has a higher value than, say, pi business as usual. So BAU, business as usual, for those who've seen that. But the idea is that, people do something in a particular domain, and you might want to show that if we tailor optimally, we can do better in that domain. There's also this idea of conditional value. So we might say, well, what's the performance if we took our estimated regime pi hat, and there should be a sub n here, pi hat n, and we deployed it. So we estimate a rule or a policy, and we say, now we're going to use it in the population. What's its performance? And so in that case, we'd have v hat of pi is the expectation of y times the indicator A equals pi hat of X divided by the propensity, but the expectation is only over X, A, and Y, but not over pi hat. So this is a random quantity, right? Because it's saying condition on the policy you've learned. If you were to deploy it in practice, what would its performance be? And this is relevant for evaluating the performance of a learned rule or a learned regime. So you get data, you estimate the policy, and then you go deploy it. How will it perform? And then something in the middle is the average performance. So if you look at, say, Vn, so notice there's no pi here because this is really the argument to this is an algorithm. That's what would be the input to this. But Vn is the expectation of V of pi hat. So what you do is you average this over all data sets of size n that are used to construct pi hat. And that would be the average performance. And so the IPW characterization here would be the expectation of V pi hat, which is the expectation, which would be this should be a pi hat here, expectation of this thing here over pi hat. Okay, and I'll fix that in the updated version.
So that's like the expectation over your algorithm, what type of pi opt will it estimate, and then what would be the performance?
Yes, this should be a hat. You're right. Yep. Thanks, Emma. That should be a hat. And then this is over this thing here. This expectation, this bold E denotes expectation over the data, over training data. So the inner expectation, the P, is like over new draws of X, A, Y, and the outer one is over training data.
And if the algorithm had some stochasticity, it would also be over that. Is that
That's right. Yeah, that's actually absolutely right. Yep. That's right. And oh geez. I'll just write an algorithm because if I write stochastic, it'll just be unreadable. Alg. Okay. Yeah, that's right. All the other uncertainty. That's right. Okay. Other questions? Okay. Oh. So the average performance inference target is about getting a baseline for your algorithm. So or just comparing two algorithms. So we might say, if you look at like, recently there's been some work on like inference for cross-validation. They're looking at this kind of thing, which is like the average performance of an algorithm in a given domain. And so you might say, should I use one particular algorithm? I don't know, let's say some kind of policy search versus Q-learning or something in a domain. And you want to compare those two things. You might look at the average performance and see which one tends to be better on average. That would be a reason. So it's often for comparing two algorithms, if that answers your question. Okay. So one thing that happens, so we've seen this non-smoothness issue. Here we have the non-smoothness coming in through the indicator function. Right, so we have this indicator function in all three. And it turns out that these things are non-regular because of that indicator function, which again means standard methods for inference are not valid without modification. What also is kind of interesting, if you haven't seen this before, is that they don't have to agree even asymptotically. So meaning if you give them an infinite amount of data, those three criteria don't have to be equal to each other. And so we need to be very careful what we mean when we talk about inference for the value. So just to illustrate this point, let W, just to make the notation more compact, define W to be Y over the propensity score, and I'll assume this is known. I'll assume it's a clinical trial or something, so this is known. Then we can write V of pi hat to be the expectation of W indicator A X transpose beta hat. So I've estimated beta hat using least squares. So this expectation is only over W, A, and X, but not beta hat. And I can multiply inside this indicator both sides by root n, and I can also break it up by whether or not X transpose beta star is equal to 0. So if it's equal to 0, I can multiply by root n, and I can subtract off beta star. That doesn't affect anything. And so what happens now is if I take the limit, I get convergence and distribution to this thing, which is expectation over W, A, and X of W indicator A X transpose Z. So this expectation is not over Z, greater than 0. Indicator X transpose beta star is 0 plus a constant. Sorry, this thing here is going to be beta star. I don't know what's going on with these slides. This is the beta star here. So the point is that this Z is here. And so this limit, no matter how large n gets, it goes to something in distribution. right? So Z is, in fact, normal 0 sigma squared, sigma, where sigma is the asymptotic variance of beta hat. And so what we see is that this thing doesn't even converge to a constant. If we take its expectation, that will be a constant, obviously. And it will not be equal to the performance of beta star. And so all in this example, or just by sort of working this out, those three methods don't have to be the same no matter how large n is. So these three performance metrics are different, and they don't ever have to be the same in some generative models. Same thing happens in classification error, right? The test error, the conditional test error versus the average test error versus the sort of Bayes error don't have to coincide no matter how large n is, which is sometimes surprising. Okay. All right, so the limiting distribution of these estimators, they depend abruptly on this decision boundary, which was the set of x's such that x transpose beta star equals 0. And so now we're getting into this non-regular setting where we have an abrupt dependence on a set, and we don't know what this set is. So we might say, well, this set maybe has measure 0, maybe the x's are continuous, for example. But even still, fixed parameter asymptotic approximations may still perform poorly for the same reasons that we've seen in the max means case. And so what we want to do is look at a local asymptotic framework to ensure that uncertainty about that boundary remains even as n diverges, so that uncertainty about the optimal treatment, let's say under a linear model, persists. Okay, so how do we do that? Well, we're going to look at, again, a sequence of generative models, say Pn, such that under Pn, beta star n, which is just the least squares estimator under Pn, this is remember, the population analog, satisfies beta star n is beta star plus a local perturbation. So now what happens if we want to construct inference measures for a component of for one of these value functions, let's say, under these local models? How do we do that? Well, we now have our tools that we've learned, so we can look at a projection set. So let's look at a projection set for V of pi opt, where I'm really defining pi opt to be the policy index by beta star. So for any beta, let's define pi sub beta of x to be the sign of x transpose beta. So notice this is a rule indexed by beta, so that the estimated rule would be x transpose beta hat. The optimal rule, as we're calling it here, would be x transpose beta star. And let's define V of beta for any generic beta to just be the value of that policy indexed by beta. And our goal is to construct a confidence interval then for V of beta star. That's our goal. So let's define V hat of beta to just be the empirical analog. So it's just Pn of W indicator AX transpose beta is greater than 0. So here I've used the fact that A is coded -1,1, so that this is the same as A equals sign of x transpose beta, of course, and that's the rule. So it's also the indicator that A equals pi beta of x. Same thing here. And then for any fixed beta, you can show that root n V hat beta minus V of beta is asymptotically normal with mean 0 and some smooth variance function sigma of beta, sigma squared of beta. This is if you hold beta fixed. So that's really important. So if beta were fixed, then this would be no problem. In other words, if I gave you beta star in a sample of data, you could estimate the value of the policy indexed by beta star, and you can get a confidence interval. And sigma squared of beta is given here. This is sort of a familiar expectation of a term minus its mean. So we could then construct a confidence interval for a fixed value of beta as follows, right? So this is a fractor z and 1 minus alpha of beta, v hat of beta minus a normal quantile times the estimated standard deviation divided by root n. Same thing, only plus that quantile scaled by the standard deviation over root n. So this is a standard confidence interval. We're using the asymptotic normality here. So if we had a fixed beta, if we had a fixed policy we wanted to evaluate, there would be no problem. Of course, the issue is we don't know beta star. And if we plug in beta hat's a 1 over root n perturbation of beta star, and these confidence intervals will no longer be valid because they're non-smooth. But what we can exploit here is the fact that we're using OLS, so it's easy to construct a confidence interval for beta star, which we can do, again, using a wall type interval. So here, fractor f of 1 minus eta for some eta, just a set of beta such that n beta hat minus beta transpose sigma hat inverse beta hat minus beta is less than some kind of chi-squared quantile or percentile. And if we let omega be eta plus alpha, so just a reminder, alpha is the error level of this confidence set for V for a given beta. And eta is the error of this walled interval. Then a 1 minus omega times 100 projection confidence set for the value of the policy index by beta star is the union over all beta in our confidence region for beta star of our confidence interval for the value indexed by beta star. So again, this is easy to construct. This is standard walled interval. You get these in closed form. And this will have the correct coverage even under a local generative model under some mild assumptions. So here I'm going to be slightly more formal with the assumptions. We're kind of ratcheting up the technicality, I guess, in this tutorial. But so here, I just wanted to give a sense for the kind of assumptions that you would make if you wanted to make this a little bit more rigorous. So I'll assume that there are finite moments. This is generally true in any application. There exists some epsilon so that the propensity score is bounded away from 0. So the probability you assign treatment 1 or minus 1 given every x is no more than, oh, what was beta, please? Okay, so we had a question, what was beta? Beta is the parameter indexing the Q function. And we're looking at, and here I'm focusing just on the contrast part. Sorry, I should have said that, and I think I didn't. I'm focusing only on that contrast part. So there's two parts. There's a main effect, and then there's an A times X transpose beta. And I'm focusing only on the contrast part currently. Thanks.
And Eric, what is the, I mean, I see some relationship between the simple projection you did for there were a bunch of means, and then you did the ellipsoid and then projected, and this, but somehow there is an extra loss here, like eta and alpha are getting added, but there it wasn't. Like, could you just?
Yep, we're gonna prove it right here. Exactly right. That's exactly what's gonna happen. There's two extra pieces now, and they're gonna show up as additive. So maybe I'll just talk. Let me just talk through the interval first, and then I'll go through the assumptions, and I'll go through the proof. Does that sound like a good idea?
Yep.
Okay, thanks. So the point here is that if I were to give you beta star, if beta star were given to us, then we can construct a confidence interval for the policy indexed by beta star simply by doing this, right? And we can estimate this just by putting an average over the data here and here. And this is a normal quantile. And this estimator is just this average over the data. So we can definitely, this would be easy to construct if beta star were given. Of course, we don't know beta star. So what we'll do is we'll construct a confidence interval or confidence region for beta star. And then we'll take an interval like this for every beta in that confidence region and then take a union of all of them. And the way we can screw this up, or the way that we can make a mistake, there's two ways. One, our walled interval might not capture beta star, or it might capture beta star, but still this confidence interval might miss, right? This is still a 1 minus alpha confidence interval, so it has some probability of missing. So the probability that one of them misses is bounded by the sum, and so our coverage will be this, our error level will be the sum of the two. Okay, thanks. Okay, so just some quick technical conditions. So sigma n, this is the variance under of beta hat, asymptotic variance of beta hat under Pn, strictly positive definite for all n. And then the way that we get these what's different here is that, you know, we're talking only about this parameter beta, but there's an entire distribution. So we're going to talk about a class of local alternatives or local generative models that sort of give us what we want in terms of beta, but are otherwise unspecified. So for any s, there's a sequence Pn such that if we look at this distance between Pn and P, there exists some real valued function V indexed by S, such that this difference in squared mean goes to 0. So this is a technical condition that's, I don't want to really get into, but it's, if you're interested, it's in the paper, and it's also in, say, standard empirical process text, like Van der Vaart and Wellner, for example. But under this Pn, beta star n equals the argument of Pn of y minus the Q function, so this least squares estimate. And we'll assume that beta star n equals beta star plus s by root n. And also we'll assume that these moments are also finite, uniformly bounded for all n under Pn. So basically we're just assuming that we have a generative model where the OLS estimator is a 1 over root n perturbation of beta. Okay, so now what happens? Let's look at the coverage. So the point here is that if we assume A1 through A3, so this is regularity conditions, and that the data are drawn under one of these local generative models, so that is the true beta is a perturbation of beta, motor perturbation of beta star. The question is, what paper is this in? This is in a paper by Labor and Chen. It's a review paper on generalization error. It's probably the easiest one if you look up. I can put it at the end of the slides too, but yeah. So there's a review paper on generalization error that we wrote that's in something.
And Eric, yesterday we were talking about realizability and stuff like this, and you made a comment that let's posit a linear model, but your conditions on the previous slide are not assuming that things are linear. Am I correct?
That's right.
You're doing inference with respect to the projection.
Yeah, that's correct.
Okay, just wanted to make sure that we're not necessarily assuming that things are.
Yeah, so we're nowhere assuming that things are linear, but we are assuming we want to do inference for the best linear model that we would fit if we had an infinite amount of data. That's right. Yeah, thanks. Yeah, we're nowhere in here are we using linearity of the Q function, or the true Q function, that is, or the true conditional mean. So I'm going to define Vn of beta star n to be the expectation of W indicator AX transpose beta star n is greater than 0. So again, that's just the value of beta star n under Pn. And for any omega and 0, 1, let that be arbitrary. Then the probability that Vn beta star is in our projection interval is at least 1 minus omega plus little o1. And the proof is trivial, but I think it helps to illustrate what's going on here, which is the following. So we look at the probability that we don't cover. So the probability that the value under Pn of beta star n is not in this interval. Well, let's break it up into two cases. One, it's not in the interval, or not in the set, and our walled confidence interval didn't cover beta star n, or our did cover beta star n, or it didn't cover. Now in our first projection set, this term was just 0, but now that's no longer the case. If we look at the probability that our confidence set for this thing to miss, what has to happen is, in this first case, well, our confidence interval for the value of beta star, given beta star, treating beta star as fixed, has to not cover. So that's what this is saying. That's what this fractor z is as a function of beta star. That's the value, that's the confidence interval for the value as if beta star was given to you, right? Why is that? Because remember, this thing here is a union of all those sets, and we're saying beta star is in there. So it's got to include the set with beta star n plugged in. So we can miss by having this not included, or we can miss here, which says, you don't include and our beta star n is not in our walled interval. So we'll just bound this above by the probability that the walled interval misses, which is this here. And the error of this is no more than alpha. The error of this is no more than eta. And so the result is alpha plus eta plus little o1. So a lot of notation for a pretty simple idea, which is just we don't know beta star. So let's just construct a confidence region that contains it. And because beta star is a regular quantity, all this the walled interval also works under local alternatives. And similarly, for any fixed beta star, the value is nicely behaved. And so, or for any fixed value of beta, the value is nicely behaved. And so it's regular. And so when you put them together, you get correct coverage, even under local models. So one thing that came up was, how do we improve this? How do we make this less conservative? Is there some way to change the projection? And that's the projection interval, and that's exactly what we're gonna do now. So this can be extremely conservative in some settings. So, and the reason is that it doesn't adapt to the number of points near the boundary. So if for example, X transpose beta star was bounded away from 0 with probability 1, so it was totally away from this boundary, then we could just bootstrap. There'd be no issue. There'd be no points in the boundary. We could have just done the bootstrap or normal approximation. There'd be no problem. So what we want is some kind of adaptive projection that only is conservative when you have points near the boundary. So how do we do that? Well, we use a pretest to identify those X values that are somehow near the boundary. And then we apply a projection interval that only affects those points. Okay, so how do we do that? Well, so now we've seen these kind of pretests, and we've seen kind of these bounding type ideas. So hopefully this isn't too unfamiliar. But so what we're going to do is we're going to sigma hat n be an estimator of the variance of root n beta hat minus beta star. We're going to assume that X transpose sigma hat X is bounded away from 0 with probability 1. So this thing is positive definite. These things aren't identically 0. And our test statistic is going to be X transpose beta hat divided by this quadratic form. So the idea is that this thing will be small when X transpose beta star is close to 0 and be big otherwise. And this is our test statistic for the hypothesis for each X that X transpose beta star is 0. Right? So if this is large, then we're going to reject. And if it's small, then we would fail to reject. And we take a sequence of critical values, say lambda n, and I'm going to define this quantity bold Gn of beta prime to be P of W indicator AX transpose beta greater than 0 when the test statistic is large. So I have the first argument is going in here when the test statistic is large, and the second argument is going in here. It's the same quantity, except for the test statistic is small. So the idea is these are kind of the nicely behaved parts, right? These are points that are far from the boundary, and these are points that are near the boundary. And so what I want is the projection interval to kind of only affect this part, if we can help it, or if we can do that. So first thing to note is that V of beta star is just Gn of beta star. So if you plug in beta star for both. And if all the points are far from the boundary, then Gn beta star beta doesn't depend on beta, meaning it doesn't depend on the second argument because this term here will be identically 0. So what we've done is we divided the value into the sum of two parts, one where points are near the boundary, one where points are far from the boundary. And now we're going to see if we can do a projection that only affects the second term. Questions on this?
Yeah, there's actually a question, well, maybe not on this, but on maybe just the general, even the non-adaptive projection interval. It's a two-part question. Are there any finite sample results? And second part is about the dimension. How does the width scale with the dimension of beta star?
Oh, yeah. So good question. So of course there is work on like concentration type results, which are very general, right? I mean, they tend to be uniform type results, and the consequence is that the coverage that we get tends to be, from a confidence interval coverage point of view, tends to be very conservative in a lot of those cases. So, the coverage might end up being just identically 1, whereas we might want it to be 90% or 95%. So they do exist, but they are often made under such general conditions. So they can be stronger results in some sense, but then on the other hand, they can be more conservative. And whereas here, it's like what you're trying to do is get a confidence interval kind of at the generative. If you imagine sort of instead of having a uniform result over all generative models, it's sort of at the true generative model or in a neighborhood of the true generative model. Although we will show some uniform results later. What was the second part of the question, or what was that? Scaling with n, yeah, with p. So in general, these things become more conservative as the dimension grows, but it also depends critically on how much mass there is near a boundary and how much noise there is in the data. Yeah. Okay, so what do we do here?
Speaking of you mentioned like you can build confidence sets based on concentration inequalities, which are very general, or you can do this asymptotic business that's based on normal approximations and the sort of classical distributional theory. And I see that this stuff is used for inference, right? I'm trying to produce confidence intervals for the optimal value or for whatever I'm interested in. And these, we saw in the tutorials earlier this week that we use these concentration inequalities maybe in an algorithm itself, upper confidence bound type algorithms, to maybe even direct the exploration, maybe direct the data gathering. I've never really figured out like I mean, both are objects that somehow are trying to trap a quantity of interest inside. I might use concentration inequalities or sort of limiting distribution theory. I will have obviously more wider intervals if I use concentration inequalities because they're general. But is there any inherent reason that one set of techniques are used for one sort of use, or is it just communities being more familiar with tools? Like, do you have any opinion on that?
I think these grew out of So why I guess maybe why is one used so heavily by one community and another by the other community? Well, so all of this stuff that I'm talking about today comes out of this goal of estimating the sampling distribution of a thing, as opposed to bounding an error. So it comes out of that culture of thinking like, what's the sampling distribution? And now we're getting at bounds and things which are moving towards this idea of some of these inequalities. But I also think there's this idea that like here we really want it to have certain operating characteristics, so 95% coverage, because if it's too wide, then we lose power and so on. Whereas in some contexts, it may be enough to just rank order actions. And so if everything is shifted up, it doesn't matter, right? I mean, as long as you sort of get the direction right or the ordering right, then the algorithm might still perform optimally. And so that's also a difference that if everything's conservative in the same way, then across the actions, then maybe it doesn't matter from a selection point of view, but from an inference point of view, it may make a difference. But others, I don't really know. I mean, in my own, spare time for fun, I've tried to look at like whether UCB or other things could be improved if you had like, confidence intervals that were not based on bounds, but based on estimates of the actual distributions. In some cases, it seems to make a difference. In other cases, it doesn't. I don't know.
Oh, I see. Interesting. Thanks.
Okay, so now we have this quantity that's indexed by beta and beta prime. So let G hat just be the version of this you would get if you just put an empirical expectation here. So just average over the data. And you can show then that under those conditions, lambda n goes to 0 and n times lambda goes to infinity. Then for any arbitrary beta, under either P or Pn, ret n G hat of beta hat, comma beta minus G n of beta star beta converges to a Gaussian random variable with mean 0 and some variance that depends on beta. So the point here is, for the first component, the part that was sort of far from the boundary, I could just use a plug-in estimator for beta star. So I just plug that in. So notice if we were in one of these situations where everything was far from the boundary, and this term had no effect, I would just have a plug-in estimator minus the truth, and that would be it, right? So it'd be what we do in normal statistics. But if we do have points near the boundary, then this does play a role. And so the idea is it adapts in that sense. And so we can use this now to conduct inference. And in particular, we can have a projection set, but the projection set might only affect this second term. So how do we do that? Well, under that lemma, we can construct a confidence interval for G beta star for fixed beta. So we want a confidence interval. So this beta is treated as fixed, but we plug in beta star here, which I call fractor M, 1 minus alpha of beta, G hat, beta minus your normal quantile and standard deviation, so on, G hat, beta plus the same quantity. So it looks a lot like we did before, only now we have this sort of beta hat plugged in, with the idea being our union now is only going to be over beta, and therefore will only affect that second term, that non-smooth part. Okay. And here rho hat is just some estimator of the variance of this thing. Is an estimator of this, which is the variance of G. So then an adaptive projection interval for Vn of beta star n, which I'll call Jn of 1 minus omega, would be the union over all beta in our wall type confidence interval of these sets here now. So to see why this is going to be less conservative, potentially, as I mentioned, if all the points are far from the boundary, this thing here doesn't depend on beta at all. And what you would end up getting is just a regular old confidence interval where you plugged in beta hat in place of beta star. On the other hand, if all the points were amassed in the boundary, now you do it back to the regular projection interval. So it's in between the two. And the exact same proof shows that you get consistent coverage under either Pn or P. Okay. So adaptive projection intervals, the same form as a projection interval, and the proofs are equally trivial. I didn't show the proof here, but it's exactly the same. If points are far from the boundary, then this is a standard confidence interval based on a normal approximation, and it limits conservatism to the non-smooth parts of the functional. And this adaptation to non-smoothness is a theme for inference in RL, at least as far as this talk is concerned. So this is going to be a key thing: is how do we make it so that we are conservative only when we need to be, or only kind of where we need to be. So now a slightly more challenging problem, but also just to illustrate a bounding technique here, is how do we get confidence intervals for v of pi hat? This is often more relevant in like precision medicine type problems where we've estimated a policy and we want to know how well it would perform if we use that on patients. Now notice that the estimand itself is random, right? This is averaging over kind of future subjects or future decisions, but not over pi hat, right? So this is a random quantity. So if we have a random estimand, then what do we mean when we say to construct a confidence interval for it? Well, a valid 1 minus omega confidence set, let's say Cn, for v of pi hat is just a random set that satisfies the probability that v of pi hat is in C is at least 1 minus omega plus a negligible term, where the probability is over both the randomness in pi hat and in Cn, and also, as Emma pointed out, if there's randomness in pi hat, if it's for a stochastic policy. See, I'm showing my bias. We're like, and often looking at deterministic policies in my world, but yeah, that would be over all the uncertainty. And so both this thing and this are random. So both the estimand and the confidence set are random, where normally when we talk about coverage, we have the estimand being fixed and the set being random. So this is what we mean when we say a confidence set. In the paper that this is all drawn from, we also show conditional coverage given pi hat, but I'm not going to talk about that today. Okay, so how do we construct a bound for this? Well, we can let Tn be the pretest statistic that we use in the adaptive projection, so the same test. And if we look at root n v hat of beta hat minus v of beta hat, it's just root n p n minus p of w indicator ax transpose beta hat greater than 0. And we'll just break that into two pieces. One where points are far from the boundary, that's this first term. And one where points are close to the boundary, that's the second term. And this should be less than or equal to. So covering all cases here. And now what I'm going to do is I'm going to bound the second term, right? So I'll write this as less than or equal to the first term plus the sup over all beta and RP of the second term. Now, we had looked previously at taking sort of constrained sups, but here, because it's inside an indicator, it's invariant to scale. And so if you take any ball that contains 0, you can take all of RP and it doesn't matter. So this bound is a little bit simpler in structure. It's easy to see this is an upper bound because if I just plug in beta hat for beta, I get back to this first quantity, right? So it has to be an upper bound. And so this is an upper bound on this quantity, and you can get a lower bound by taking an inf here. And so these bounds turn out to be smooth, and so you can bootstrap them to estimate their quantiles consistently, and thereby construct confidence intervals for v of beta hat or v of pi hat, which I've been using interchangeably here. So in particular, for any alpha, let L hat be the alpha over 2 percentile of the lower bound, U hat the 1 minus alpha over 2 percentile of UN. Then it follows that the probability of V hat of beta hat minus this quantile of root n less than or equal to V of beta hat less than or equal to V of beta hat minus L hat over root n. So the probability that these two bounds contain the conditional value is at least 1 minus alpha. Okay, and that makes sense because you took an upper and lower bound, and if you take the upper percentile of the upper bound and the lower percentile of the lower bound, those have to be bounds on the percentiles of the thing that you're bounding. But both U and L depend on the unknown generative model, so you couldn't actually compute this thing. So what do you do instead? Well, you just estimate those using the bootstrap. So you can bootstrap these bounds, and because of that sup or inf, in fact, the bootstrap is consistent. And you can show that that you can consistently estimate these quantiles and thereby construct a valid confidence interval. So the bootstrap analog here would be you replace the empirical average with the bootstrap average, the true distribution with the bootstrap, with an empirical expectation, beta hat with its bootstrap analog, the test with its bootstrap analog, and so on. But you can compute this quantity then and compute its percentile that way. Okay, so this gives you sort of a bound-based approach for the conditional value that will hold under both fixed and local alternatives. Questions on this before I continue?
So can you go back to the coverage definition? Just wanted to ask you a clarification question. So as you said, this probability on the left-hand side is over all of the sources of randomness. But you mentioned, I think, in one of your comments that you also have procedures where you modify this definition to be conditional with respect to like the actual pi hat that you've picked. Isn't that the more, or maybe I'm not misunderstanding, isn't that actually the more natural definition to say, I estimated a rule, now it's no longer random. I mean, just give me some interval that traps its value.
Yeah, it's just, it's a more complicated object. And it's the only time, I think it's the only time I'm talking about conditional coverage here, and I just didn't want to open that can of worms, so to speak.
I see. What the can of worms is due to, what's the complication?
So then you need to show that the coverage, one way to get it would be to get some kind of joint distribution of pi hat and then the confidence set and then back out the conditional coverage. But in general, conditional coverage is harder to show if you have.
Oh, I see. Because the distribution of pi hat itself is involved, which is it's not an easy object to think about.
Yeah, that's right.
Okay, I see.
Yeah. This Cn and the distribution of pi hat are they're dependent on each other.
But again, in terms of your comment about scientific goals versus mathematical practicality,
you're calling me out on my comment. Yeah, you're right. You're right. Although you are right. That is probably more of interest scientifically. I think that's probably the right thing to do. But I didn't work that out until recently. And so my brain has always been on this, which is also what you'll see in the literature. So you're right. This should be given. Yeah. But it is gnarlier. So yeah. Yeah, that's a good point. Okay, so we tried to use the ideas that we learned from the max means case for inference for the value. We looked at a projection set, adaptive projection set, bound-based sets. The same ideas apply to infinite horizon case, and I will say a little bit about this, but not too much. But how do we bridge those two? Well, least squares just become solving a Bellman equation. So, where you would have used a standard CLT to get a nicely behaved estimator, now you use a Martingale central limit theorem with a Martingale estimating function instead of just sort of normal equations for least squares. But in general, you get the behavior there, and then you can still apply these ideas. And so it just becomes more complicated, but the tools are the same. There's still, Bernstein inequalities and CLTs and stuff that work for the Martingale difference case. It's more complicated, and so the ideas get buried a little bit in that, I think.
And if one wanted the details, where can one find this? Like worked out the whole thing with the Martingale CLT. Like is it in your book? Or?
No, it's not in the book. I think, I don't know. I mean, I look at like Lie and Way from like 1981. It's like, I will say I do show kind of how you would get it. And then some of the estimating function stuff from Gadambe and that whole line of research. I will say something about that. I don't know that anyone's ever bothered to write it up directly. I mean, Ashkan has doesn't have inference under these kind of conditions in his infinite, if you know that paper, which is greedy GQ, but kind of from a stats point of view. So there's a paper in Biometrica by Ashkan Edrafe on Q-learning in infinite horizon cases with function approximation that is based on an extension of greedy GQ. I think it's a nice paper, and it sets everything up in terms of these estimating equations, which then you could use this stuff for. And I have two slides on that. But then the Martingale convergence stuff, I think, is scattered across these estimating functions literature and the old stuff on like stochastic, what do they call it? Regression with stochastic predictors. Does infinite horizon case equals multi-stage? I'm making the distinction between finite horizon multi-stage and infinite horizon multi-stage, or indefinite horizon multi-stage at least. So I will talk about a two-stage case, but then also talk about the infinite horizon case. So the difference there being that in the finite case, often we won't exploit any Markov structure, but we'll use kind of just regression-based dynamic programming, whereas in the infinite horizon case, we will use the Markov structure, and then we'll we'll have to use that structure to then construct an estimating equation. So that was a question in the chat. Okay. We are slightly making up for time. So now I want to talk about a two-stage problem. And this is going to focus on dynamic treat regimes, well, at least the first part, just to motivate the kind of questions we're trying to answer. But then it'll just get back to basically finite horizon dynamic programming. But so dynamic treatment regimes, this is the tool used commonly in precision medicine or personalized medicine. And there's lots of examples where we want to tailor treatment to individual patient characteristics. So I listed a bunch here, basically all chronic illness and even acute illness. It sort of represents clinical practice as a multi-stage decision problem. That's how it models. That's how we model that decision process. And there's often a trade-off between immediate and long-term outcomes or proximal distal outcomes. Dynamic treatment regimes are just the formalization of this decision process as a sequence of functions, right? So, or decision rules. And so you have one decision rule for every time point or one that sort of comprises a policy. And a decision rule is just a map from the information you have to a recommended treatment. And the goal is to optimize some cumulative clinical outcome. So we're going to look at finite horizon decision problems, and we're not going to assume that they're a Markov, but we will assume we have IID data. So just to give you a sense for what these things look like, this is an actual DTR for patients, school-aged children with ADHD, estimated from data in a clinical trial. And this is the kind of thing we want to produce with the algorithms I'm going to discuss and the kind of inference we're going to want to make. So again, I want to get back to the method, so I'll try to go quickly here. But so this is just a simple decision rule that you start in this upper left, and then you follow the arrows. So it says, has a child had and tolerated prior medication? If yes, assign them low-dose medication as their first treatment. If no, assign them low-dose behavioral modification therapy as their first treatment. Then you look to see if they're a responder or not. And that's operationalized, but I won't get into that definition. But if they are a responder, then just continue whatever you were giving them, right? So it's working, don't change it. But if they aren't a responder, then you look to see, are they adhering to the treatment? If they are, and they started off on low-dose meds, intensify meds. If they're not adhering, then add behavioral modification therapy. And similarly, you see kind of parallel structure here, which is if they are adhering, then intensify behavioral modification therapy, and otherwise add meds. Intensify means go twice a week instead of once a week. I thought at first maybe it just meant talking more intensely, but that's not true. So all right. So what kind of inference do we want to make? So suppose we take data and we estimate a rule like this, and I'll talk about the form of the data in a bit. But if we estimate a rule like this, well, what do we want to know? We want to know things like, well, which variables are important for tailoring treatment? So what do we need to measure on a patient to decide what treatment to give? Is an estimated rule like the one I just showed you better than standard of care or business as usual? Which first-line treatment is best for a given patient? This is something that people are often interested in because I think it has clinical meaning. But the inference is complicated by this non-smoothness problem. Again, non-regularity causes the sampling distribution of estimators not to converge uniformly over the parameter space. And so this is one of those cases where we, like the max, where we don't have any regular or asymptotically unbiased estimators for this or other estimators that are of interest that I mentioned here. And so, as we've seen, standard inference methods perform poorly in small samples. So just a roadmap for this part of the tutorial. I'm going to look at two-stage Q-learning, and I'm going to talk about asymptotic bias reductions, which is something that shows up that we haven't talked about yet. And are they worth it? And then locally uniformly convergent confidence intervals based on bounds, bound-based intervals. And then I'll just say one thing on, so this is the other place that I talked about this. I'll say one thing on conditional confidence intervals, which was a discussion that we had in a paper that we wrote. We had written something and then there was a discussion and the discussion of the discussion. But in terms of setup, we're going to look now at data from a randomized clinical trial to make things simple. Local asymptotics, as we've already argued, to study the finite sample performance. We're going to use linear working models for the Q functions, but we won't assume that they're correct. And the same idea applies to other estimators. So those like there are, like say, direct search type methods and other things. The same issues arise and the same intervals apply. Okay, so here's the setup now. So it's slightly more complicated than before. But now for every subject, we have a trajectory, x1, a1, x2, a2y. So I indexes the subject, I equals 1 to n. They're drawing an IID from some distribution p. X1 is the information you have before the first treatment is assigned. A1 is the first treatment. So now I'm coding it 0, 1 because it'll be convenient to do that when talking about the bias. X2 is interim subject information. So information collected during the course of the first treatment. A2 is a binary second treatment, and Y is an outcome measured at the end of the study or the end of the observation period. So that higher is better. And we'll define the history H1 to be X1 and H2 to be X1, A1, X2. And so a policy or a strategy or a dynamic treatment regime here is a pair of functions pi1 and pi2, where pi_t maps the history to the action. So the support of the history, the support of the action, under which a patient presenting with HT equals little ht would be assigned treatment pi_t of HT. So it's just a map from history to actions, and it's a two-stage decision problem.
I think we are supposed to take a break.
Oh, sure. Okay, yep.
So I don't know if this is a good, because I thought you were introducing new notations. Maybe it is a good breaking point.
Yeah, maybe we should stop here, and then I can kind of review this, and then we can go. Yeah, I mean, when we come back, I'll review this again, and then we'll. That's a good idea.
Yeah, that sounds good to me. I think good. That's your point.
And I don't see any unanswered questions anywhere, so I think we're good with that. Just one, I just wanted to have a clarification from you, Eric. You said that in this multi-stage setting, you will not assume any Markovian structure. Like basically these x's, x2, for instance, given x1 and x8 could evolve in any way, and the y, especially the y, the sort of the analog of the reward, this could depend on everything in all sorts of complicated way.
That's right.
Okay.
Would a Bayesian methods be useful for problems that you've discussed? Yes, absolutely. The Bayesian methods are useful in a number of different ways, especially the adaptive randomization. It makes a lot of intuitive sense to use them there. And also, I think there's some really nice work in kind of non-parametric based specifications to like having like implicit groups of patients that are somehow similar. There's the natural updating as data accumulate. I think one of the reasons that I'm not talking about Bayesian approaches here is that the inference does become harder to get to guarantee frequentist sort of properties is more complicated. And so that's one of the reasons I'm not talking about it. But I think because, for example, what can happen is the prior can end up kind of like suppressing the non-regularity issue. And so Phil David has a paper on this from the 90s where he looks at treatment selection problems, which are like the max of means problem, and what happens in a different sort of Bayesian approaches if you're not careful. And so that's another issue, is that you also need to carefully kind of construct your models to ensure that you are going to be robust to local perturbations. But yeah, I think there's a ton of potential there. Or hybrid methods where you use the sampling distribution as a surrogate for a posterior, and then you do things like Thompson sampling, or you do things like maybe some kind of safe Thompson sampling or safe updating. I think there's a lot of potential there. Okay. Any other questions?
Kind of related to that, I mean, so we were talking about adaptive clinical trials before when you began your talk. I keep hearing things like Bayesian adaptive clinical trials. Is that just a kind of a methodology within adaptive clinical trial design?
Yeah, so there you might have a posterior probability that a given treatment is optimal, given a patient's characteristics and all the data you've seen so far. So, or it may be something like just straight Thompson sampling in that sense, or there might be some other kind of adjustment where you truncate the probability, or you have some other kind of adjustment. And then there's also the Bayesian. There are also Bayesian adaptive designs where you look at the posterior information gain basically as a function of what you have, the information you have so far. So if you could do like active learning, and you could select X's, for example, you might recruit patients that maximize information gain for your model. So you look at the distance between the prior and the posterior under like each patient you might recruit, or like or treatments also potentially. Yeah.
I see. Thanks. So I think, yeah, we can stop now. The Zoom will just be on. It usually just stays on. And this break is a longer one because approximately corresponds to lunchtime in the Pacific time zone. So we'll just reconvene at, it's 2:30 here. So it's 11:30 in California. So 12:30 there and 3:30 in Eastern.
Okay. Is this at the right level so far? Are we is it too fast or too slow, or is it okay?
Based on the questions, I feel we're going okay. Like, I think as long as people are still asking questions means that someone's following the material.